Hey guys, welcome to the second lecture for SYSC 2100, and today we're going to be talking a little bit about data abstraction. So data abstraction is basically what is described as the walls, and it really is there to make our lives easier as programmers, and we'll get into it and we'll see exactly why that is. So first let's talk about modularity. So what modularity does is makes a large program simpler, and how does it do it? It just controls the interactions between different parts of your program. It makes the flow of your program a lot easier to read, or it makes it a lot smoother, and it's just a really nice thing to have in any programming language, really. So let's talk about a couple concepts within data abstraction and modularity, I guess. And so the first one we're going to talk about here is procedural abstraction. So what procedural abstraction does is basically it separates the purpose of the implementation or of the of a part of a program from the implementation. So what do I mean by purpose? Well, I'll do an example right after I talk about information hiding, and then we'll see exactly what I mean by that. So information hiding is what it hides parts of your program, the implementation details of part of your program, and it can only be accessed within one of your modules. So we might know this in Java or any kind of object-oriented language as making something private. We make things private within, say, like our instance variables, and we would make them private so that they can't be accessed by programmers from other parts of the program, which is a good practice within object-oriented programming specifically. So let's do this example here to help further explain kind of what procedural abstraction is, and just in general a little bit how data abstraction works. So what I want to do here is square a number, right? So right on the right side here, I have a class that's called MathOps, okay? And here, MathOps, I want to use its square function, and it just squares squares a number. So to do that, first I need to create a MathOps object. So let's say this is my creation, and I'll call it M. Okay, and let's say I want to I want to square the number. I'm going to make it a double, and I'm going to call it x, and I'm going to give it a value of 4. Right? So now I want to access the square function. Now, when I normally do it inside this part of the program, I won't know exactly what the implementation of this is, but I know exactly what it does. It squares the number. So what this is doing is it's separating the purpose and use. You see here, we know the use of this function, but how does it do it? Well, we don't know. We're just going to use it. So let's say we have our M object, and I want to access its square function. And I'm going to do it on the number x. There we go. Now I've called on this function, and now it's going to return its result. And we know that it's going to give it a value of 16. Okay, so that's just an example of how abstraction works. Let's talk about some actual applications that they use within programming languages. So let's talk about abstract data types. So what we know is abstract data types is a collection of data, and this collection of data has a certain set of operations that can be used on it, and it's usually outlined through this abstract data type exactly what the data manipulation does. So usually abstract data type doesn't actually store its own data. That's left to the data structure. The data structure is what actually implements the different operations that can be done on data. So we might know a data structure to be a array list, or say a linked list, or a or a set. We know those are different types of data structures. But ArrayList, for example, it implements all the all the methods of a list. So a list is known as an interface that outlines exactly which operations can be done on the data within the array list, but the list doesn't actually implement it. So the array list is what actually takes those methods and then tells exactly how to do it. And the programmer can't see exactly how it's done. So all it has to do is call on one of those uses, and usually it's like procedural abstraction. You know exactly what those operations are going to do, but you don't know how it's done, and that's how procedural abstraction works. That's how just abstract data types and data structures work together. And you can see that right here. I drew out a little diagram where here's our program. I want to call on something to be done to my certain data structure, or the data structure that's holding the data that I need to use. So I request an operation, and here I've got a list of different operations that can be done on the data. So you see that, okay, here, say I want to add a value to my data structure. So here, I've called on add, it does it, okay, right back through here, and it returns the result of the operation. This is usually your interface right here that implements or that outlines the different methods or functions that can be done on the data structure. And then here's your data structure, like I said, that implements exactly what we have to do, or implements how it is done. And this is what I mean by when data abstraction is the walls. It basically allows you to access, it just makes it easier to access exactly what or what you want to do with the data structure. It makes things really simple. So earlier I mentioned lists and array lists and stuff like that. So let's do an example of what's happening here using lists. So basically the most common type we're going to be using is a list of some sort, and all it does is just stores information of the same type. Remember that. So say if you define something as a list as an integer list, then it's going to only store integers, and it stores it so that the front of the list has nothing pointing to it, and the end of the list is not pointing to anything, but anything in the middle has something pointing to it, and it is pointing to something. This is known as the head of the list. This is the tail of the list. I'll get rid of this not to confuse you, sorry. Okay, and anything in here has something pointing to it and something that it's pointing to. So let's do a little example here. Here I've written out kind of a little pseudocode thing for how of a practical use of an array list. So here I've defined my array list, and it's called numbers, and it's the type integer. So once I've created my object that is a new array list, I wanted to add something to it. So I added the number 7. Sorry, magic numbers, I know. But here, now I want to go through my array. So here's a simple for loop. Now I'm going to go through my array list, and I want to print out the number that from each index in the list. So I get in here and I call the temporary variable that where the number object I call on its get method to get each number, and here I called on its add method to add the number in. So the get method gets the number that I want, and the add number adds an object to the list. And now I print it out and I get an output of 7. Cool, right? So what exactly happened? So again, we can go back to this drawing, but let's keep it a little more practical to here. So here we have our code, our code is this stuff. And our code called on add and get. So we requested add and get right here. And you can see it's in this interface right here, so we know we can use it. So now it's going to say, okay, now let's roll into the data structure that we're going for, and our data structure is an array list. So this is an array list type and it's called numbers, and we know that. And it does the add operation on it first, calls that back, and gives the result, which is the result was actually adding it to the data structure. And then we called the get method. So we requested get, here it is. We got the data structure, it gets the number 7 from here, and now it brings it back. Here's our result, and it printed out a result in temp, right, using temp and the print method.